travel is supposed to broaden the mind, this journey is to measure the cosmos, to set our position in the broadest context of all, the universe. Far from city lights, and with just a whisper of cloud, the Milky Way straddles the sky. This delicate band of light is our home in the cosmos. For when we observe the Milky Way, we're looking sideways at a disk of stars. That disk is our galaxy, our island universe. From above, the Milky Way is a spiral, a family of some 150 billion stars. We belong to that family. Our Sun is one of these stars. It lies 2/3 of the way from the galactic center. The Milky Way turns like a Catherine wheel, great arms spiraling outward. Within one of those arms, the Sun orbits the galactic center once every 225 million years. Like a city, the center shines brightest of all. Veiled in gas and dust, it seethes with energy. But our neighborhood is suburban, quiet stars leading ordinary lives. The Sun is no exception. It's yellow, average, and middle-aged. For an idea of scale, light from the Sun takes 8.5 minutes to reach Earth. Light from the nearest star takes 4¼ years to reach us. Astronomers call the distance 4¼ light years. The Milky Way is 100,000 light years across. From our position to the galactic center, it's 30,000 light years. The constellation of Orion rapidly loses shape as we hurtle through space. Stars that seem close together from Earth are really hundreds of light years apart. But in the vastness of our galaxy, we're still close to home. This group of young stars, the Pleiades, is 380 light years away. Closer are the Hyades, older, dimmer stars, at 150 light years. And although from Earth it seems to be in the Hyades, this orange giant is less than half the distance. Aldebaran, over 100 times more luminous than the Sun. Sirius, the dog star, less than 9 light years, the brightest star in our night sky. Barnard's star, a red dwarf, 2,000 times dimmer than the Sun, and on its way toward the Sun. As it sweeps by in 10,000 years' time, it'll be our closest galactic companion. But for the time being, the nearest is Alpha Centauri, a trio of stars just 4¼ light years away. To see where stars are born, we must first look at another galaxy. This is M83. Glowing pink in its spiral arms are regions of starbirth. In our own galaxy, these are such nurseries. They're called emission nebulae, clouds of glowing hydrogen streaked with black dust. Stars fire up where material clumps. Lower left, a brilliant young star in its dusty cocoon. And here, white hot, groups of new stars. The black dust in this nebula is scattered far and wide, dispersed by the winds of fierce new stars. Stellar birth is violent. Blowing together, an array of energetic infants clear this gigantic bubble in a red nebula. Young stars blow a hole 12 light-years across at the heart of the Rosette Nebula. The more massive the star, the shorter its life. Average stars, like our Sun, live long. Massive ones die young. Voraciously consuming their fuel, they become red supergiants, bulging to hundreds of times their original size. This one, Antares, is enveloped in a cloud of its own material, a reflection nebula. Antares is so big and diffuse that it leaks into space. A star like Antares, far more massive than the Sun, swells as hydrogen runs out. It switches to helium and other elements, but equilibrium is lost, and it grows. Radiation pushing out beats gravity pushing in, and that's its undoing. The red giant puffs into space. The core exposed, it collapses to become a white dwarf. And here's the real thing, a dwarf in a stellar smoke ring. Astronomers call it a planetary nebula. This one has wings, blown into the shape of a butterfly by ferocious winds. Another with more extended lobes, the legacy of a red giant. One of the most beautiful is from the demise of the giant that gave us the Helix Nebula. "300 light-years from Earth, the Helix is our nearest planetary nebula, the white dwarf at its center, visible in this actual picture. The white dwarf lower right leads a busier life. Its gravity draws material from a companion. But when the matter reaches critical mass, it explodes as a nova. Both stars survive, and the process repeats. Bigger stars make bigger bangs. This red supergiant has 10 times the mass of the Sun. The Sun lives 10 billion years. This star just 20 million. It's fast, furious, then finished. The explosion is a supernova. Here, in the Crab Nebula, a supernova is observed from China in 1054. Its debris is the nebula. Within the Crab, a pulsar survives, spinning 30 times a second. It's a super-dense relic collapsed from the original star. Around it, a disk of material and matter jetting from the poles. Trained on the Crab Nebula, the Hubble Space Telescope reveals more. Time-lapse shows shockwaves from the pulsar, particles spinning from the disk at close to the speed of light, whipped into space by the whirling magnetic field. And here, matter from a polar jet hitting slower material in the Crab. The elegant tendrils of the Cygnus Loop, another supernova remnant. To exit in such glory, a star must have at least 8 times the mass of the Sun. Only superstars go supernova. With 100 times the mass of the Sun and venting great clouds of material, a pre-supernova symptom, this star, Eta Carina, may be the next to blow. And when it does, the remnant will collapse beyond the pulsar stage. It will be so dense, it'll form a black hole. Birth, life, and death in our galaxy. But there are far more galaxies than there are stars in the Milky Way. nearest galaxies, two mini-galaxies called the Magellanic Clouds. The small cloud is to the center, the large at the right. In the large cloud, in 1987, a supernova blows. In fact, this supergiant expired 160,000 years ago. It's taken that long for the light of the flash to reach us. Andromeda is our closest major galaxy at over 2 million light-years. At 10 million light-years, the Silver Coin Galaxy, a spiral like Andromeda, and like our own galaxy, the Milky Way. We probably look like this. A spiral from above, the M83 galaxy, also at 10 million light-years. We're now at twice the distance. The light of this galaxy takes 20 million years to reach us. This one, 35 million years. And from the beautiful Sombrero Galaxy, 40 million years. Vast distances, but all these spirals are relatively close to us. This galaxy, Virgo A, is different. It's shaped like a basketball, an elliptical galaxy, one of a cluster up to 60 million light-years distant. The Virgo cluster is part of a supercluster of about 1,000 galaxies. Galaxies cluster because of mutual gravitational attraction. But how do we know this? How do we measure the cosmos, or even the distance to our galactic center? Our galaxy is one of 30 in a local group. That group is part of a cluster, and the cluster part of a supercluster. Superclusters form strands across the universe. To help construct this model, astronomers use what they call standard candles. There's a standard candle in this galaxy, a pulsing star that brightens and fades as regular as clockwork. It's called a Cepheid variable, a star whose brightness varies as it expands and contracts. This one is big and bright and pulses slowly. But this Cepheid is smaller and dimmer and pulses faster. The speed of a Cepheid's pulse is directly related to its intrinsic brightness. So if we know the distance and true brightness of these nearby Cepheids, we can calculate the distance of remote Cepheids, Cepheids that appear fainter but beat with the same pulse. In this way, we know that the Andromeda Galaxy lies at a distance of 2.2 million light-years. Cepheids in our own galaxy are compared to fainter Cepheids here in Andromeda. But ground-based telescopes detect Cepheids only out to 15 million light-years. It takes the Hubble Space Telescope to see them in this galaxy at 55 million light-years. And in this galaxy at 80 million light-years. Beyond that, another sort of standard candle is necessary. Astronomers call it a Type 1 supernova. It occurs in a two-star binary system. A white dwarf, a star at the end of its life, swirls at the center of an accretion disk. It draws material from its partner. When the dwarf reaches the mass of 1.5 times our Sun, it explodes, a Type 1 supernova. The flash intensity is always the same. It's our new standard candle. From Cepheids, we know the distance of this galaxy. But because it also has Type 1 supernovae, that gives us the distance to our new standard candle. That candle, a Type 1 supernova, lets us measure up to 100 times deeper into space. But our journey has barely begun. In the 1920s, the American astronomer Edwin Hubble discovers our expanding universe, galaxies traveling outward in all directions. The evidence is in their light. As a galaxy speeds away, the lines of its spectrum move increasingly toward the red. The farther and faster a galaxy recedes, the greater the shift into red. The measurement of red shift is the greatest tool in the sizing and shaping of the cosmos. It suggests that the distance to the farthest reaches of the universe is 15 billion light years. Mapping the heavens in the early 1960s, astronomers identify points of intense radio noise. Through optical telescopes, the sources appear as ordinary stars, but they can't be, for redshift puts them at billions of light years distant. They're not radio galaxies. This one, Centaurus A, is noisy, but less energetic. Nor are they Seyfert galaxies, radio sources that have brilliant cores. Seyferts are 100 times less energetic than radio galaxies and at least 10,000 times less energetic than the new sources. But all three are fueled by supermassive black holes, voracious concentrations of gravity. The black holes in the new sources are gigantic, devouring the equivalent of up to 600 Earths a minute. For those radio astronomers have discovered quasars. Quasars are superluminous. They're the most energetic objects in the universe and among the oldest and the most distant, with enormous red shifts. Our sizing and shaping of the cosmos yields yet another great discovery: colliding galaxies. This is such a merger, the antennae galaxies. Simulated on computer, the two spirals don't really collide, but swing through each other like cosmic pendulums. Their gravitational interaction ejects two great tails, like the antennae of an insect. The merger triggers a starburst. New stars are born. The antennae are 63 million light years away. At their center, a firestorm of starbirth. Another cosmic collision. The intruder galaxy has passed right through the larger one, disrupting its structure. Here's a real picture of the same effect. It's the Cartwheel Galaxy, scrambled as one of the small galaxies on the right plowed through. In this collision, neither galaxy emerges. Instead, a supergalaxy is formed. In 10 billion years' time, that's possibly the fate of our own galaxy. We collide with Andromeda. We live in a mystery. It's called the universe. We can measure it, analyze it, observe it, even explore it. But what is the universe? How did it begin? Why did it begin? And how might it end? Some people reject the idea that it started with a Big Bang. Cosmologists generally accept the theory, but while they can explain how, they have no idea why. This is the theory of the Big Bang. From a single cataclysmic explosion, everything springs. From a speck smaller than an atom emerge matter, space, and time. It's blindingly hot. In the first microsecond, the universe expands to the size of a galaxy. It's a particle soup, growing bigger and bigger. It's so hot, energy spontaneously generates matter and antimatter. They annihilate each other and start again. Matter wins by 1 part in a billion. Matter is to dominate our universe. Protons, neutrons, electrons. The universe is now 1 second old. It's opaque. We can't see a thing. But physicists work it out. This expanding maelstrom seethes with subatomic particles. Atoms are about to form. At 3 minutes from the Big Bang, they create the first chemical elements: hydrogen, helium, and a trace of lithium. For 300,000 years, the cosmos is a fog. But as it expands, temperatures drop. Our universe becomes transparent. For the first time, light and other radiation speed across space. A telescope can't show us the early universe. A particle accelerator can. This is an atom smasher. Electrified particles are crashed into each other at approaching the speed of light. For a split second, we're in the earliest universe. The collisions reproduce, fleetingly, the subatomic particles that abounded immediately after the Big Bang. The veil is lifting on the opaque universe. In 1965, Americans Robert Wilson and Arno Penzias detect the first radiation of the visible universe. The horn behind them picks up a microwave hiss from every direction, an echo of the Big Bang at minus 455 degrees Fahrenheit. As the universe has cooled, that signal, originally in ultraviolet, has shifted to microwave. It's called cosmic background radiation. This is COBE, the Cosmic Background Explorer. It makes sense of the microwave hiss. Like a supersensitive thermometer, COBE takes the temperature of the universe, first removing the solar system, then the Milky Way. What's left is an ancient temperature chart. From the first radiation of the visible universe, evidence that a primitive structure has emerged. That structure takes 1 billion years to develop. Ever expanding, galaxies in clusters, clusters on strands, the voids between growing wider and wider. Here, mutual gravitational attraction draws groups of galaxies into clusters, and clusters into superclusters. How galaxies form is a puzzle. We know how a supercluster like this evolves, but its collisions and mergers make it hard to unravel the earlier history of individual galaxies. Computer simulation confirms that the evolution of a supercluster is a violent affair. Some galaxies spin right out of the system. Gravity conducts a chaotic dance. It may last for billions of years. Young galaxies in the very early universe appear small and irregular, the product possibly of the repeated merger of smaller clumps. Those infant galaxies bear little resemblance to a mature spiral like this. Current thinking is that galaxies grow from smaller aggregations of matter in merger after merger. Subsequent development like this is better understood. Galactic interaction is the norm. Often it's cannibalism, big galaxies ingesting smaller ones. It continues to the present day. But what is the present day? How old is the universe? If it's expanding relatively slowly, we can deduce that the Big Bang happened some 15 billion years ago. If it's expanding rapidly, then the universe is younger, between 10 and 13 billion years old. Winding back to the Big Bang is one way. Another method of aging the universe is to look at stars hovering outside the plane of our galaxy. Such stars form groups of up to 1 million. Called globular clusters, they contain the most ancient stars in the universe. By analyzing their light, the age of these stars is initially set at up to 15 billion years. But the first windback results put the age of the universe at only 11 billion. These stars can't be older than the universe. The satellite Hipparcos helps resolve the issue. Its mission is to measure the distance of thousands of stars with unprecedented accuracy. Hipparcos employs parallax. It measures the shift of a foreground star against a more distant star. It does so from opposite positions in Earth's orbit of the Sun. The accuracy of Hipparcos is like measuring a golf ball on the Empire State Building from the other side of the world. Hipparcos proves that certain stars are 10% farther away than we thought, making the universe between 13 and 15 billion years old. Hipparcos finds that globular clusters are also farther away, making their stars younger, at between 12 and 13 billion years old. The older the universe, the slower it expands. So, could it stop and reverse? Maybe, but one theory suggests the expansion of the universe will go on and on, till, like a firework, momentum runs out. The universe will be dispersed, bleak and lonely. The theory of the Big Crunch is more dramatic. When expansion is exhausted, the universe teeters and reverses. It could only happen if there's enough matter in the universe. Matter creates gravity. Only gravity can orchestrate such a terminal crunch. There may be enough matter, for 90% of the universe is thought to be invisible. No one has ever seen a black hole, for nothing, not even light, escapes such gravity. Like black holes, 90% of the universe is invisible. Astronomers call it dark matter. This hidden mass is undetectable at any wavelength, from gamma rays to radio. With 9/10 of the picture obscured, our ideas of the universe could be quite wrong. Dark matter may be largely responsible for the development and structure of the universe. The problem is, most of that structure is invisible. Two stars orbit a common center of mass. They have a mutual gravitational attraction. We don't see the gravity, but we see its effects. The gravity of dark matter affects the rotation of this galaxy. Its spin is measured by the colors of the Doppler effect. Results show that outer parts of the galaxy spin much faster than its visible matter justifies. The cause is dark matter. Probably a hidden halo of up to 10 times the visible mass accelerates the galaxy. But dark matter shouldn't be confused with the dark clouds that pepper this galaxy. They're just visible dust. The matter we seek tugs invisibly on these stars. And it hints at a presence in these clusters of galaxies. Their interactions suggest up to 100 times more matter than we see. But what is dark matter? Is it dead stars, or failed stars, or black holes? Or is it exotic subatomic particles? This is the visible cosmos as we know it. The nature of dark matter and its part in shaping our universe remain two of the greatest mysteries in cosmology. A superstar draws matter from its smaller partner. The big star dies in a supernova. But the partner survives, still orbiting, still losing matter. For the superstar is now a black hole. In the real cosmos, we'd see the surviving star apparently orbiting an empty space. It's a clue used by astronomers to detect black holes. This is another. Although invisible itself, a black hole distorts light in space at its rim. Approach too close, and you're spaghettified. A black hole is a collapsed star of such density, such gravity, that from within the rim, nothing escapes. To form a black hole, the core of the exploded star must be at least 3 times the mass of the Sun. But imagine Earth as a black hole. The mass of our planet is compressed to just 3/10 of an inch. It's so dense that light cannot escape, and nothing travels faster than light. But light can be bent, and it helps us find dark matter. Here, light from a distant quasar travels to Earth. Put a big object in the way, and our picture distorts. The object might be a galaxy with lots of dark matter and enormous gravitational pull. That gravity creates a crazy lens. It tugs on the light of the quasar, bending and multiplying its image. The picture we get on Earth is 4 images of the quasar, with the lensing galaxy at the center. The degree of light bending reveals the amount of dark matter in the galaxy. When the lensing object is less symmetrical, it smears light. The blue arcs are far-off galaxies, distorted by the cluster in the foreground. But the principle's the same. Gravitational lensing enables scientists to weigh dark matter. In the Milky Way, shrouded by the stars that crowd our galactic center, is a ring of gas. It has the mass of 30,000 suns. To many astronomers, such a swirl is evidence of only one thing: the pull of a massive black hole, a throat at our galactic center that swallowed 1 million suns. Galactic collision is thought to spawn supermassive black holes. Like celestial dancers, 2 galaxies merge. A supermassive black hole is formed when the galactic cores unite. This is Centaurus A, the marriage of two galaxies, a white one shaped like a basketball and a dark one that we see edge on. At their single heart is a supermassive black hole. It has 1,000 times the mass of that hole in the Milky Way. And here's another, just as big. A supermassive black hole is surrounded by an accretion disk. Subject to irresistible gravity, matter swirls inward. Some matter jets at right angles to the disk, saved at the brink by the shock wave around the central vortex. Every hour, the equivalent of 4 Earths is consumed. This is an even bigger supermassive, a hole with the mass of 2.5 billion suns. It's at the center of the galaxy Virgo A. A great plume of material ejects across space. Here's Virgo A from the Hubble Space Telescope, the jet plainly visible. And this from a telescope on Earth. But the most incredible black holes are linked to quasars. Quasars burn at the center of remote galaxies, so fierce and bright that they outshine the galaxies themselves. Quasars are fueled by the hungriest black holes, supermassives that consume the equivalent of 600 Earths an hour. These are Hubble pictures. Quasars are among the most luminous and powerful objects in the universe. Albert Einstein, the great 20th century physicist, predicted many of the effects of supermassive objects. His general theory of relativity explains how bodies not only bend light, but distort the space around them. Our universe ripples with the push and pull of gravity, the exertions of supermassive objects. A black hole is the ultimate distorter. It so bends space and light that we've no idea what happens inside. It could be a wormhole to other parts of the cosmos, even to another universe. A quasar, the core of a distant galaxy, an image in both visible light and radio. Take out the visible, and radio reveals what it brings to the picture, especially the jet. An optical picture of the galaxy Centaurus A. Radio shows it's in turmoil, the aftermath of a galactic collision. A pulsar, a tiny superdense star spinning 30 times a second. With radio, we see its powerful radiation beams. To astronomers, infrared is important. It picks out warm cosmic dust. But, like ultraviolet and the longest radio waves, relatively little penetrates our atmosphere. By and large, only visible light gets through. Most invisible radiation is absorbed by our atmospheric shield. To overcome the problem, detectors operate in Earth orbit. This is ISO, the Infrared Space Observatory. ISO must keep cool or be blinded by its own emissions. Anything hot radiates infrared. Veins of circulating liquid helium absorb heat and vent it from the craft. ISO is the coolest laboratory in the universe, minus 450 degrees Fahrenheit. But infrared pictures are hot. Here in the constellation of Orion, infrared unveils vast clouds of gas and dust, a birthplace of stars. In ordinary light, the Large Magellanic Cloud, a galaxy very close to our own. In infrared, it displays great wafts of dust where stars are born. The Andromeda Galaxy in ordinary light, and here in changing wavelengths of infrared. By highlighting clouds of starbirth, infrared reveals Andromeda's spiral structure. Within our own galaxy, ISO gathers radiation from clouds between stars. Its long-wave spectrometer specializes in the job, imaging nebulae in the pangs of stellar birth. Still in infrared, but closer to home, ISO tracks a comet, its trail like condensation from a jet plane. In ordinary light, a comet's heart is obscured. But infrared gets through, and to the shells of dust that surround it. ISO, an eye on the invisible. By contrast, the Hubble Space Telescope is famous for the visible. But Hubble has peripheral vision too. Infrared to one side, ultraviolet to the other. It's like stripping the veneer of a cosmic portrait. In ordinary light, a Hubble detail of the Orion Nebula. Pierce the dust with infrared, and Hubble uncovers cocoons of young stars. Again, in ordinary light, this Hubble picture hints at the next stop on the spectrum. The blue halo is from hot young stars radiating ultraviolet. The Andromeda Galaxy in ordinary light. But in ultraviolet, clouds of hot gas where massive stars die young. Time-lapse of the sun, ultraviolet unmasking its churning surface. Shorten the wavelength to X-rays, and there are the hottest, most energetic regions, plus the corona, the searing atmosphere of the sun. The night sky as we see it, and as it is in X-rays. At the pivot of two galactic jets, Hubble identifies a massive black hole. The Andromeda Galaxy, and evidence that it once consumed another. Hubble discovers a double core. In the Whirlpool Galaxy, it spies a suspected black hole. And here, the remnant of a supernova. The Pillars of Creation, one of the most spectacular pictures ever taken of the cosmos. It's part of the Eagle Nebula, where stars are born. A dying star in the Cat's Eye Nebula. In gamma rays, a panorama of our galaxy, the Milky Way. The hot band across the center, cosmic rays colliding with interstellar gas. The Milky Way in X-rays. In infrared, showing lots of dust. In the wavelengths of radio. And in the radiation we know best, visible light, just part of the cosmic orchestra, but nonetheless exquisite.